This is a principal component analysis. So what is the principal component analysis? In many real-world situations, we find a data set with large number of variables. Actually, our example will have only few, but I have experience has about 500 different variables. It was a medical data. It's about the organ transplant data. So we have a bunch of data for the donors. We have about bunch of medical data of the recipient also. So actually there is so many information. So we cannot create the linear regression or any statistical model using 500 variable. Even though, yeah, keep adding more and more, yeah, I know we can get even better and better accuracy, but however, I don't want to handle 500 independent variable, right? So some case we want to reduce the number of variables. Still, when you drop a lot of the variable, you lose the accuracy also. So can we minimize number of variable? At the same time, I can increase my accuracy, right? So sometimes the number of variable even exceeds the number of observation. This is sometimes it's possible. Your variable is 500 and then you collect only 300 data set of 300 observation, then you cannot create mathematically you cannot find out all the coefficient because you cannot find out the 500 coefficient using 300 data points. So that's the problem. Or but most of case these days, because we have enough number of observation. However, I don't want to use like 500 independent variable, right? So can we reduce some of them? Yeah, we can eliminate using the model selection. We can drop some of them. We can add, and then we can find out this is the best combination. But can we do better? So this is about that. So principal component analysis is trying to reduce the number of independent variable, but physically we are not reducing, but mathematically we can reduce the independent variable. Okay, so dropping the variable, we lose the valuable information. So can we not losing the valuable information by, but still we can drop to the reduced number of independent variable. So principal component analysis is useful dimension reduction technique. So here the dimension reduction technique is trying to reduce the number of independent variable. Okay, so we want to have a simple model, simple predictor model. So we don't want to use a lot of independent variable. However, I want to have the correct high accuracy model, right? So this will show you how can we reduce. So basically PCA is actually it's kind of unsupervised data mining technique. So unsupervised means you cannot tell this is actually machine learning or data mining technique has two different things. One is a supervised and the other one is unsupervised. So supervised learning has all the data point has a correct answer, then we trying to learn. But unsupervised data mining or unsupervised machine learning is we don't know what is the exact answer. Yeah, I don't wanna talk about a lot of the supervised learning. Usually the supervised learning is classification. Problem is usually the supervised learning. We have to have our data set already has labeled. which means it also has the correct answers. And then when there's a new data comes in, and then we're trying to make a classification prediction. However, unsupervised learning means our past data also doesn't have what is the correct answer. So that's what we call the unsupervised learning. So what we're trying to do is to select a relatively small number of principal components that drive most of the pattern found in the data. So we want to use a small number of independent variable, and still I want to have a high accuracy. Okay, so clustering is one of the example of the unsupervised learning. And also we can use a PCA with the supervised learning methods, linear regression, and the logistic regression, where the large number of predictor variable can be substituted with a small number of principal components. So basically it's the same. Large number becomes the small number here. So we are creating, so here the principal component is the new independent variable, new predictors. Can we create our original predictor using this one? Can we create a new predictor so that we can use only few of them, still we can maintain the high accuracy? So yeah, let's talk about what is the principal component. Principal component is let's say we have n observation and k variables, so we have a k number of independent variable. We find the sequential sequence of the principal component. Actually we can make a m, but maximum you can create is a k number of up to k number of principal component. If you create more than the k principal component, then there will be one of the principal component will be perfectly linear combination of other two principal components. So that's why we cannot create more than k. So principal component will be the weighted linear combination of original variable. So this is a linear combination. Actually, without weighted word, linear combination means we just multiply certain number and add up to all the original variable, and then that form a principal component. So the weights are derived using the eigen decomposition, but we don't know. I don't want to go over the linear algebra here. So since we will use R, so R will do all the complicated calculation. What I want to know is what the principal component is doing. So what does it mean, the principal component? What is the principal component analysis? Rather than understanding all the detailed calculation, but we have to have a clear idea what is the principal component here. Okay. So this is actually the ordered. What I mean is the first and second and fourth, that this is the ordered. So as a result, you will find out the first principal component, second principal component. But first one is the most variation, and second is the second most, and so on. So this is order. The first one is most important, and second one is second important, and so on. So let's take a look at the example. This is the case of the contains the 37 candy bars. It's a different type of the candy bars, and it has a calorie, fat, and protein, and carbs, and so on. Okay, and then we will show how the single principal component can capture most of the variability between the two variables, fat and protein. Let's look at the fat and protein only, because the handling for the four variable, we have to draw like a 4-dimensional chart, so it's gonna be hard. So let's look at only two variable, fat and protein. Here, this is a fat, right? Fat is like 18, 1 kind of number, and protein is 5, So protein, this is a protein, and this is protein, and this is the fat. Okay, so you can see this is the plot, but what if we just change our axis to here? Because this variation relative to this variation, this is a way bigger, right? This variation is way bigger than this variation. So if we have to take only one variable as a predictor, if we take this one, actually this PC1 will be way better predictor than the fat only or protein only. Okay. So PC2 is the relatively small variation here. PC1 has a high variation. So instead of using only fat or only protein, actually we can use the PC1. So how can I create the PC1 is that we can create this line is y equals, this is a PC1 actually, PC1 equals certain number, right? Just like a regression. Fat plus a beta 1, beta 2 times protein and plus beta 0, right? And then we created this line, and then each data point will be calculated on this PC1. What will be the value here? So this point we will have a certain protein and certain fat, and then plug into the number. Then we can find out the position on this PC1 axis. Everybody has this value. Okay, and using this value, if we use like a linear regression, we will get a way better result.